Okay. So yeah, so that's good that it quickly arrived. It converged. That's what's called converging. So it converged quickly. The one that we're gonna do now takes like 20,000 iterations or so, I think. All right. Yeah. So it's recording, right? And so we're gonna look at the next example. So okay, so this is I'm gonna close this. I'm gonna go back to table of contents. So we're here in NIO. We're gonna click on this. And these examples, so I'm trying to create different folders for different applications. So for these, they're under this folder, Civis, and they're gonna be here. So usually when I'm working on something, I create like run one, run two, run three, so I don't lose any error that, any error I make in something, I can always go back. So I'm currently at run 4, I think. And so this is the one that you should use right now. But I may be improving on this a little bit over the next few weeks. Okay. So I just want to start kind of with the output so that you guys know where we're going, right? So the essentially this code is just optimizing for one, but it works in batches. I'm just keeping it to one. So it's more intuitive than looking at 32 different things. Okay, so essentially the model, see, I have a little check that says all constraints were satisfied. So that's good. I know that it did it. Essentially, what I wanted was this input. These are the metrics, right? 0, 69, 33, 29, 0, 1,449, and 204. This is my input. Like that's the thing that I was searching for. The final output was this one, and the target output was this. So just like in the previous example, the target output was 0.80, and this was 0.79, and this was some vector of 3 with values, the same thing. Okay, you want to stress that. But this code and the previous code works for batches, no problem. I mean, you can generate millions in a week or something. All right, so notice what it did. So in this case, I was looking for an output where all the values were greater than these values. So you see I needed value for the first one, greater than 70, for the second one, greater than 1,800, and for the third one, greater than 2,600. Do you guys see that? And so it produced 90, 1,910, 2,679. So as you can see, it's not precise, right? But it is physical. And also, I could have done a better job by having better constraints and losses. So that I'm just going to give you an example here, and you guys can expand on this without a doubt. The loss here is a little bit more complex than usual losses, but not that much. Does this make sense, guys? So you can see, so somebody would hopefully look at this. Now, both the inputs and the outputs are constrained, as you, Matt, brought up, so that it can't create like crazy non-physical values. Because obviously, if I said greater than 2,600, well, a million is greater than 2,600, but that's a non-physical thing. So these constraints in this type of problem are definitely necessary. So some knowledge of the domain. But you can see it stayed within reason, 90, 1910, 2679. So one person hopefully would conclude, well, that's physical. Do you see what I'm saying? And if you run this input through the model, you get something similar to this output. Do you guys see that? So that's key thing, because remember that in step 1, when we train the model, that model, what it is becoming is like an oracle of that problem, right? It's something that knows the physics of that problem given the data. So it's data driven. Got it? So this is all this work for just these little lines here. Okay. Now, the losses that you guys create could probably be better and so on. All right. So we're going to start this problem and take a look at it. It has a lot of similarities from things we've been doing already this semester. I'm going to use Colab for this one. We don't need GPU. You know, the CPU is fine. New notebook. Oops. So one thing, sometimes when I'm doing things, I like to use like a utilities file that I import so that, you know, it's neater code and things like that. So I encourage you, if you'd like, to use this .py file and modify it. It's got a lot of utility functions that might help you. Okay. So I've moved like a lot of the scaling and all that stuff to this, hopefully to help out. But you can always modify the code in this .py file. All right. Anyway, so our new Jupyter notebook will need now to import this file. So you guys need to download this file to your computer, the py file, so that you can reference those functions in your code. Okay, so I have here, so we're going to need to link, I think I already have it. We're going to link it to, I'm going to link to my drive. Okay, so there it is. I want to see. Here it is, .py. I have it available. You may need to click on this upload and upload it there, and then the notebook should be able to find it, right? So we can demo that if necessary. All right, so let's just start. You guys understand what I'm saying? Everyone with me? Okay, perfect. So let's just start. Let's start with just getting that functionality of being able to import the .py file. Okay, so remember, I'm going to be exploring this run for. Now, unfortunately, for this example that I'm doing, which is a really nice example, I'm using proprietary data of this furnace. So I can't make that available to you guys, but I have also created this one, energy regression data set. So you can use this instead. It's not going to give you the results that I have, right? But it's the same dimensions and everything. So your code should run with it. Got it? Everyone with me? All right, so you will need this file as well. Okay. I already should have that in my drive. So if I go to drive, be in here. Yeah, it's this one. So I have this data, which is of the simulation of a furnace, but it's not my data, so I can't really make it available. All right, so let's start. Okay, so just to give you some insight, the variables for this example are going to be things related to inputs, something called the PCI rate, something called the NGI rate, which is natural gas. So it's the rate of natural gas that goes into the furnace. That's important. The H2 temperature, O2 is oxygen, right? So these are these knobs that I keep doing. So, you know, what is the amount of oxygen, conditions, and the win rate, something called the PCI rate, H2, and natural gas, right? So these are some variables. I think that's 7 variables. And those variables then are, we train a model um, that has to do with top gas temperature, hot metal temperature, raceway flame temperature, which you can think of as the nozzle at the bottom of a furnace that's blowing, something, like I think natural gas. And so what's the temperature of it? It's like a little jet, that affects the process. Okay. So we want, essentially given, we have some inputs, some outputs. Okay. All right, so that's the description of it. So now I got all these libraries here. So the same familiar libraries that we've been using all semester. And I think, let's see, is there anyone that's going to break here? So it should all be good. We don't need Onyx, any of those, because this is not something that we deploy with Onyx. All the libraries worked. Here we will comment out a few things. We don't need XGBoost for this one. XGBoost, it's not neural, right? There's no stochastic gradient descent, so you can't really optimize it. It'd be nice if you could, but it doesn't work that way. All right, so I'm going to comment out this one. And don't worry if we don't finish this one. I have allocated today, this hour, and the hour before the exam to finish this exam. Okay, so we may not get to the end. All right, so we got sklearn. These Onyx ones we don't need. These also we do not need. All right, so we run this now. Oh, the Boston thing. Yeah, can ignore Boston. Boston is a data set that has some bias historically, and so it's not recommended that we should use it anymore. All right. So that worked fine. We've got our libraries. So this is, the code that you guys can actually use, right? So I would think if you're going to start somewhere for your project, it's probably this one. Unless you want to start from the baby one and just kind of build up. That's fine. Yeah, sure. I commented out anything related to Onyx. So Onyx, also the Boston one, and then Onyx here, and this Onyx here. So essentially, I just left zip file and the sklearn ones. Okay, great. So we've got that one. Now, here comes we got to import the utils file. Okay, so it's not finding it, no module name utils. So if that happens, I think I already have it in my downloads, actually. Let me see. But you would download it. So is it here? Yeah, so I already have it in my downloads. You would bring it from the website, right? So you would go here to run for, and you would download this file to your downloads, plus the regression file, the data itself. Oh, and also let's do a sign-in sheet today for participation. Anyone have a spare page that I can borrow? Piece of paper? Do you have one? Can you just pass it around and sign in? Yeah, it doesn't matter. Sorry, get some participation points. All right. All right. Yeah, so I need to link that. So the way that I think uh, this can work is you click on this, upload, and we go to the downloads. We click on PDF, open, click OK. And I think there it is now. So hopefully now it's able to find it. And it did, right? Did everyone get that? So that's a little trick I learned the other day. So if you have like a file that you need to bring in for classes and things, it should work that way. All right, that's great. So once we have this, we are in good shape. I do need the path to my data file. So my data file is this one. So I'm just going to copy. This is similar to everything else we've done. Keep in mind what we're doing is in the step one is exactly what we've done several times this semester, just training the model. So I'm going to go over here. Yeah. Where is the PY file originally? It's in this NIO to the downloads. I put it in the downloads. And then how did I upload it to Colab, you mean? Yeah. So to upload it to Colab, you click on this, and then you go to this button here, the little arrow that means upload, and then you just find that file. That's it. Yep, great. Yeah, and so now, so we have the library with all the functions that you can use. Now let's just run a few like checks to make sure everything checks out, and then we can load the data set. So this would, just initializing some variables. Did I skip a part here? Oh yeah, I skipped. So I didn't instantiate it, right? So I brought in the library, but you also have to instantiate it, this file. So that's going to be this. So I'm calling, this PDF shaping object. So you instantiate, and there we are. So now we've got this object with all the utilities that we want to add. It'll just keep your code more organized, more succinct, make your life easier. All right. So now we can proceed to run these checks. So I'm going to hit, so that worked out fine. Okay, so that's good. Run this one also. Just initializing variables and things like it's how I check that everything is good. All right, great. So the next step should be to bring in the data set. And you can see this is my data set that I'm using to illustrate this problem. Because I know this actually, I've had this verified and the results worked and everything. But you guys here have to use the other data set I provided, which has the exact same dimensions, just the data is obviously a little bit more randomized. This one. Make sense? And I also used ChatGPT and told it, get me some energy data. So it has some distribution of, and that's actually, ChatGPT is really helpful at generating data sets of things. So whenever you're looking for a data set of something, you can just ask it and it'll give it some properties. All right. So I have that. So now let's load in the data, but I need to specify this path, of course. Okay, so Okay, so it loaded the data set. Great. And that's really good. Okay, so now we just visualize the data set and we will talk about it a little bit. So as you can see, it has about 5,000 samples. This is what I was saying. This technique does not really need that much data. I was talking with you guys earlier that actually, let's say you have 5,000 samples, but you always wanted to have 1,000,000 samples. Well, NIO can help you to synthetically generate the data, right? You generate inputs that generate certain outputs. And these are inputs that were not in the data set before because it's new cases. You're like, what if, I want this case is a little bit different from the ones I had in there. And now you just keep doing this and you could generate, I don't know, 1,000,000. I mean, there's no limit to the number. Yeah. Yeah, like that one, I mean, you can. I mean, it's somewhat synthetic, but usually those techniques just take like the mean and then randomly add something to it. This is more like the data set does not have this case of what happens if the variables are like this, then what would be the input for that? You know what I mean? Like if you're an expert in something and you can think of this has never happened, but yeah. And this is the output case. What would be the input to that? And then you do that 10,000 times, you have 10,000 new samples. Is that totally correct? I mean, you got to experiment with it, but it could be useful to you or not. You see, but that's another use case, synthetic data generation. I don't know that this can be used for LLM training, but we are getting to the limit of the text that can be given to LLMs, right? So they're using synthetic data now. That has become a big thing because it's consumed all the human generated text already. So there you go. All right. So anyway, that's another application, but here we have 5,000 samples and 41 variables. I do think if you use that data set that I provided, you get the same dimensions. Okay, and since I extract the values by, thank you, extract the values by index, then oh, you never, okay, yeah, thank you. Yeah, just sign in. Thank you very much. All right, so I want to show you then, if you load your pandas data frame here, how to index the values out of this. All right, so that's going to be a little bit new. It's a good idea to print the list of values in there. So you can just use this, and it's going to give you the number and what the variable is. So that's where you decide, okay, I want, H2I, PCI, WPI. Well, that means you need index 2, 3, and 4 in relation to FTA, which is 40, TGT, which is 27, and HMT, which is 29. Now, this example just had that, but coke rate, actually, it's a really important one. Or production rate. There's actually this one, production rate. I want to increase my production, or I want my production to go down. Do you see that? And so, that's entirely up to you, but I think if you structure your data like this, it'll work just fine. All right, so this one provides the mapping so that you know then what indices to grab, okay? Let's add a few more. Okay, so now I have this completed. Then here you can do the same thing. I always recommend doing this, especially because you'll be getting new data sets. Yeah. You need to provide different, grab a few titles and yeah, exactly. So, but yeah, so you'll have exactly different titles and, but once you have your real data, then you can make some sense of it. Okay, good point. All right, guys, so this provides some information of outputs to inputs and so on to find the correlations. This will tell you if your model is going to learn things because we are training a model, right? So initially in step 1, so you do want to know if all these correlations are 0, you might have a problem. All right, so that's fairly similar to everything we've done before. Here, we just convert the Ph.D data to NumPy. So in the past, we've been doing this by hand, but now I just, I like to just simplify. So you can just run this one. All right, and internally, all of these are being held. So here comes the important part. This part is how you grab your inputs and outputs. So once you print out the variable names, then you decide what indices you want for the input vector and what indices you want for the output vector. So if you remember, I grabbed 27, 29, and 40, right? And these are 27 TGT, 29 HMT, and 40 FTA. So these are the three output variables that I care about. And then the same goes for the inputs where I have 7. Make sense? This is how you can do the selection. Thank you. And this prints automatically for you the 7 to 3. So you got the dimensions. You know that the input is 7 and the output is 3 for this particular problem. Okay. So once that's done, we can print the shapes of X and Y from our class. So you can see 4,999, 7, and 3. Okay, I've got my inputs and my outputs. There we are. Remember that this is a regression problem, but in the past we've done ones where this is a 1. Now we're doing multi-output. Okay. So now this part you guys know how to do. This is the picking a random seed and then splitting the data into train and test. So this is exactly how we've done before. Okay, so here I split the data, a 20% split. So now I have 4,000 samples for training, 1,000 samples for testing. You do want to check the R-square of your model to see if it's good or bad, etc. Not just go by the losses. Okay. So now we convert everything to torch. So that's it. Convert it from NumPy to torch. And then we can standardize. Now, in the past, we've always standardized just the X's, if you remember, the standardization, scaling the data. But here, because you have a vector of 3 as output, which are regression values, you can also standardize those. If you remember, neural nets love standardized values, so it might improve results. But what I do in all the classes is that they actually always output a scaled and descaled version. So you always have that available. So just think of it as model outputs, not just YPRED, but instead YPRED scaled, comma, YPRED descaled. That way, for loss training, you use scaled. For inference and showing the results, you use descaled. Make sense, guys? And that's totally easy to do as well, as you will see. That's something you define in the architecture of the model. Okay? Here, these functions just generate the data loader. The gen data loader train, and then we just print train DL. That's it. So it's the same code as before. I've just wrapped it in a class to make this so that the NIO itself is the thing that distracts you. Okay? All right. So now that we are ready, we can look at different architectures. So I'm going to provide 2. There's a third architecture actually that I will give you later. I think we've covered it already. It was that F1 plus F2, if you remember. I recommend that you use that one too in your analysis. Okay? So I will just give you or create your own. That's fine too. So the first one, pretty straightforward, simple net. You can use this one. Notice I defined the inputs as 7, the outputs as 3. Obviously, this is going to change for your particular problems. Same thing as before. We create a class, simple net, and then module. It's got the constructor in it, and it's got the forward function. Okay. Notice that now we have x means x deviations, y means y deviations, because we're going to be standardizing both inputs and outputs, but that's handled by this code. And so these are already automatically generated. So I'll show you how to retrieve them. And then here, just to keep it simple, I use NN sequential. And the architecture just goes from 7 to 64, from 64 to 64, and from 64 to 3. Okay, just a simple net. Now, here is where you might want to look at some things. X comes in, and usually we would standardize it here to produce X. Then X would go into the model, and it would produce Y scale. So Y pred, right? But here I'm calling it Y scaled because I want the Y's to come out scaled in this part, but then from the model directly, or from this self here. But then that Y scaled, if you notice, is also processed. In this case, notice that the formula here is X minus means divided by deviations. Now it's going to be Y times deviations plus means. So this is descaling. Just like before we were standardizing, now we're de-standardizing. Okay? And so now I have this one standardized and this one in the real ranges and everything, 2000, 2050, and so on. And so the forward model then, what it does is it returns, if you notice, Y descaled, comma, Y scale. So now you get 2 outputs instead of 1. And that's really handy so that we can have, so it's handled internally. Any questions about this? Yeah. Why is the descaled version better for inference? Because natural gas as minus 0.3 makes no sense. But it might make sense as 150 tons. Do you see that? So that's why. And especially here with the clamps and everything, and the fact that no one's going to say, I want natural gas to be above minus 0.3. They're going to tell you, I want it to be above 1900. And I want this other variable to be above 200 and so on. So it's helpful to have both. But you don't want to train the model at those scales, as we know. So we want to descale or scale it, sorry, standardize. Make sense? All right. So guys, did you understand this, all this here? Like this, I've added this new code, and now remember the function has 2 returns. Okay? All right, so that's simple net. You can use that one. The other one I'm going to introduce today, if you remember, I've talked about this one during the semester, the residual net. You remember I mentioned this one. We've talked about residuals. They're not just for ResNets and for images. They can be used, in fact, for many other things. So the idea with ResNets, I've mentioned this before, as we start getting neural networks that are very deep, and all these matrix multiplications, what happens to the weights? 0.5 times 0.5, 0.25, 0.25 times 0.25, like 0.00 something. Eventually, it's 0 everywhere. So deep. The solution with residuals is that instead of doing this, y equal fx, as normal, you do that plus x, right? So that's the residual. We need to add that. Now, the key requirement for this to work is that if you're going to be adding these two things, the dimensions of this tensor need to match the dimensions of this tensor. So that's really the only trick that we need to worry about in this ResNet. So we're going to do that. So notice, I'm going to run it just so that it's already, yeah. So if you notice here, same idea, 7 inputs, 3 outputs. The class is called residual net. There is, in fact, a constructor init, right? The init function. And then we've got forward, right? Same idea as before. So now let's take a look at what's happening here. We still need, as with simple net, we need x means x deviations, y means y deviations. There's also this thing called dropout, which let's ignore once again for a little bit. But just, dropout is just you are dropping every iteration a few of the connections. Imagine you zero them out and then the model just learns with the remaining. So like 10% of the connections are not there for that iteration, and it has to use just 90% of the remaining ones. And you're randomly doing this over training. The idea being is that that somehow allows you to try different architectures, different connections. All right, so here's the super init for the inherited class. Same thing with x means x deviations, y means y deviations to standardize both inputs and outputs. Now the architecture here, take a look at it. In particular, let's start actually down here because this is important. So you guys have done projections, right? So we talked about what a projection is. That's a fundamental concept when we were doing the first third of the semester, tensor operations. Essentially, you can map a vector of 7 to 256 or whatever you want, right? By a simple matrix multiplication. So that's the key requirement. I'm going to keep all the dimensions at 64, but obviously the input is 7. So I can add back a vector of 7 to a tensor of 64. So what do? A projection. So simply, I create input projection, NN linear, which is going to be n inputs, which is 7, mapped to 64. And there you are. Now x is 64 by a projection, which is like what we've done before. So then the architecture here now would come in as 64. And then 64 to 64, ReLU dropout, 64 to 64, ReLU dropout, 64 to outputs, which is 3. Okay? And so, but that's essentially all that happens here. So whenever the input is not 64, it just gets this operation of the NN linear. So now let's take a look at forward. Okay? So notice here, x comes in and we standardize it the usual way to obtain x. Still a vector of 7. At this point, we run it through the projection. So it's projected. Now x is called x0 and it's 64. And that way we can add it back later. Then I have my x here into FC1. That also will get mapped to 64, goes through an activation, dropout, so that this x1 for sure should be 64. Do you guys agree with me? Okay. Then x1 goes into FC2, activation 2, dropout 2, gets mapped to x2, which is also 64. And then now notice x2 plus x0, which is the initial x without any processing, except for the mapping to 64. Questions? All right, that's a residual net. All right, this one is not very deep. Obviously, the point is to make these super deep, right? And to be able to add back at every iteration. So this is just a simple version of this. Once x2 plus x0 are added, they become xres. Xres goes through F3, which maps from 64 to 4, to 3, which is the output. Now keep in mind here, there's a little trick. The way that I'm scaling, the way that I'm processing data, the data, because this comes out as scaled, then some of the data in the training data is already the YBs, right? So that's also scaled. Or let me put it this way, that would also need to be scaled. If this Y scaled is coming from the architecture standardized, then once you compare that in the loss to the YBs, those also have to be standardized. Do you guys understand that? Any questions about that? And that's something that I'm already internally handling, is my point, with the class. You can check the code, but it should be like that. Now, this part here of descaling, this is just for inference, for visualization. So we take Y scaled with the Y deviations, Y means, and now we return both Y descaled and Y scaled so that we have it available. Okay? So this might confuse you a little bit, but just the code should be there. All right. And then I will give you a third architecture later on, or it's the same F1 plus F2 that we discussed some weeks ago, but I don't have it with me today, and I don't want to just like, so I'll double check, and I might create a run 5, which will have it in there at some point. All right. So now that I've done this, we've introduced the residual net today, so you have yet another architecture that you can use for your problems. Now let's get ready to train the model. So here, this is the residual net. It takes in, and here is, you can see the PDF shaping class is already handling calculating X means, X deviations, Y means, Y deviations. So once you run this code, it'll be processed for you. You just need to grab these whenever you need it. Okay? So you instantiate the model, and then the model here, you link it to the atom optimizer with a learning rate of 0.001, and notice here, we're back to the way we were doing it. The optimizer gets model.parameters, because the thing that we're going to update in step 1 is the weights of the model itself. Because this is a regression problem, we use standard MSE. So that's just the same. Run that one. Okay, that worked fine. And then now this is just a training function for step 1 of the model. This is what's actually going to look at all the data that you have and learn. So you're training a model to become an oracle. That's kind of how I'm trying to describe this. Step 1, the model is the oracle so that we can now ask it questions. And what's the question that we ask it? I want these outputs. Give me the input. And so it's going to think in its way and give you the, you see that? So that's why it's like the oracle. All right. So you can see here, the training is the same. We put it in model.train, 2 for loops for epoch in 1,000 iterations. And then this is what I was saying. So when we grab from train DL, we're already grabbing YB, right? And XB. We zero out the grads, and then we run XB. Is XB here standardized or non-standardized? This XB that goes into model here, is it standardized or not standardized?
Thinking through.
Yeah, think about it. That's an important one. Standardized, not standardized. Not standardized, right? Because in the architecture is where we standardize it. But I've already taken care of that in the data processing. So you didn't see it, but that should be correct. And you can look up the functions and correct or improve them in the .py file. Now, notice that the model produces pred descaled and comma pred scale, right? So which one do you use for training? Pred scale. Which one do you use for inference? Like you want to show your results to your client or something? Pred scale. And so this makes your life easier by just having this be more efficient. Okay, so pred descaled comes out, pred scaled comes out standardized, pred descaled comes out non-standardized. Now notice in the loss FN, which is MSE, it takes pred scaled, therefore YB needs to be what? Scaled, correct? But the function already did that for you, so you don't have to worry about it. Do you see what I'm saying? So be careful not to change this and understand what I'm saying here. Are there any questions about this idea? All right. So yeah, so notice after that is pretty much the same thing as before. Pred scaled, comma YB, they're both standardized, and that calculates the loss function. And then you perform this familiar loss backward optimizer step, and you print out the epochs. So if you notice over here, it starts at around 31, 12, 08. It kind of jumps around. I think I'm using the residual net. You can use the simple net or the other ones to play to obtain the best results possible. Got it, guys? All right, so that should be step one. And you can see the losses are here. Once that's done, I just print out like a few for a sanity check, if you will, of values and things like that. And then that's it. That's step one. And then we move to step two. Now, keep in mind in this version, run 4, I should have done this, but I've been working on this, so I didn't have time. We do have a test set, right? So I would recommend that once the model is trained, that you measure the performance using the R square on the test set. Got it? Just so that we have that metric that your model actually is good or bad or something like that. Okay? And if I have time, I will add that in, but that's something you can add in later. And you're on your homework, you're doing this anyway. So the only difference here, this is multi-output versus single output. Got it? All right. So the model's still training, but we can continue with our discussion. And now we are going to look at step 2. Start around here. Okay, so let's take a look. So I will add this as well, I guess. These are just, I like to, with this kind of thing, you want to check out the means and the standard deviations just to see where they are. Okay, so that's kind of recommended. So you can see here, the means and the standard deviations are actually not scaled, which is really nice, right? Because that's what you use to scale. But what's nice is it gives you some sense. So for instance, the means of your outputs are 97, 1300, and 2308. So okay, on average, all my outputs are around that. And then you have a standard deviation of around 50 versus 500 versus 210. This is actually, for this type of problem, very important to become familiar with what you're looking for, right? So I think here you should definitely look at this for your problem, whatever you're doing. Same thing for the inputs. How you know is this one has different shapes, 7. I do recommend as a good idea that your inputs and your outputs don't have the same dimension. If they do have the same dimension, that can lead to a little bit of confusion. So try to differentiate that a little bit, because when I look at this, that helps me a lot to okay, this is 7, so it's the input. This is 3, so it's the output. All right, so this one has 7. You can see the mean, so it's around 12, 18, 41, 25, 268, 440, and 198. So those are the values. Okay, And then we have the standard deviations there. So we'll print those out. Okay, so step two, the actual NIO. This is when you're going to take the model, right? Freeze the weights and start doing everything else. So there's a few functions here that we're going to have. And so we'll start. So let's see where it's at. It's almost done, I think, because I'm doing 1,000 iterations. Almost done. Okay, so let's just add these functions and then we'll talk about them. So a lot of these are just like little tricks that I'm trying to improve results. So like take C. So C is going to be the term that defines the input itself. Okay, so that's like there's going to be an X, which is the input, but that X is calculated from Z. So C is like an initial vector that is going to be somewhat random, but needs to be optimized. Okay, and then this is an operation. We can skip this for now, but notice that we just take Z, square it, take the sum of it, and multiply it by this value. So it's a way of like changing the numbers here. So we'll skip that for now. We'll need it in the loss function later. So let's look at this one also. So this is get X from Z. So as the name implies, the X input that we're going to get whenever we want to have the input is going to be gotten from this function, given that it takes in a C value. All right, some C value that goes in. This is a function called a lambda function. So essentially the way that it's written is you say lambda, this is going to be the input to it, and then this is the actual code that will process that C to return a value here. Okay, so this is also, and we'll come back to this later, but this is the clamps that I was talking about. So this is how we're going to generate C. We're going to train a C that learns to generate an X, but that it's constrained by these parameters here. So that it shouldn't go, this is where we control that it shouldn't be a million or negative, and actually it should be maybe between 0 and 3,000. Do you see what I'm saying? But we'll come back to this again because we have to like explore this with values to see what it's doing. Okay, but for now, we're just doing a high level overview of the process. Okay, so I think, okay, so it finished, which is what I wanted for this to finish. So it trained. Now we run the checks and we can see we have our means and our standard deviations for X and our means and our standard deviations for Y. Okay, so that completes step one, training the model. Now we are back to NIO. So we can run this one. This regularization we'll use later. So we can skip that for now. This get X from C, as I said, is so that we can apply the clamps. We will experiment with this one with values, but this is how a value goes in and comes out constrained for the inputs. And this also we will discuss later because it has to do with the loss function. And it's called a softbox penalty. And if you look, the trick is there's a lower bound minus X, and there's an upper bound or X minus an upper bound. So it's another way of the value should be within this range. Like I want natural gas to be between 500 and 700. Do you guys see that? But these are terms that will go in the loss function. So as we start crafting that, we will explore these three ideas. Okay. So now here is the inputs. Let's talk about this. I wrote this just as an example, this would be like the most basic way that we could do this, right? We create a torch tensor of some values here, 7 values, and we just say requires grad equal true. Remember, that's kind of what we said before. So ignore these 3 for now. We'll elaborate on them later, but here is really where we should start. However, this process, the way that I have it set up is a little bit more detailed than this. And instead, I'm using this approach. Okay. So here, the first one should be pretty straightforward. I just create a random tensor that is 1 by 7, where 1 is the batch of 1, the vector is of 7, and then I multiply, because all of these are random values, right? So each of them will get multiplied times 0.4, and then you add 0.3. So it's kind of like 0.7, but sometimes to the left, sometimes to the right. So you can control what value this is, okay? This is something I just played with to see what results I could get, okay? So that produces C init, and then C init, I'm going to run through this torch logit function, okay? And this, so what is this one going to do? Let me see. So here, let's print C init. So you can see these are the values that I generate, 0.60, 0.65, 0.58, 0.42. You can see they're somewhere closer to 0.4. Do you guys see that? You know, you kind of control that a little bit by doing this approach. You have to play with these things, okay? Like eventually you could totally optimize this, but initially that's one of the challenges of this assignment is really you play with these numbers. All right. So we did that. Then this part over here, I just want to run. So now let's say this is going to be temp val. So it's a function torch logit of cinit, okay? And we're gonna print it. Okay, and here it turns the values. What's that? No, that's fine. I forget why. Let me look this one up because I don't remember torch logit. Yeah, so it has some default value probably. And it just converts. So it returns a new tensor with the logit of the elements of input, which I'm assuming is this equation here. Input is clamped to EPS or 1 minus EPS. EPS is none. Okay, so I have EPS as none. Or there's nothing, I think. An input is less than 0 or input greater than 1. Okay. Huh. I'll have to double check that one, to be honest, guys. I don't remember what the purpose of this is. But anyway, so I'll come back to this one. Okay. But you can see it processes the values. It's got to be something with the distribution. I have to double check on that. All right, so once that's done, this value is then passed to this thing called torch NN parameter. Torch NN parameter makes it into a parameter, which is equivalent to saying that it makes it requires grad equal true. Do you see that? So that's essentially what's happening here. Okay, so we understand that we have vectors of 7 randomly. We understand that they look around 0.4, 0.5. We ran it through this logit. To me, logits just means it's like probabilities, but this can't quite remember why this is looking like this. All right, I'll look it up. And then so when we run this one, now we have our Z. Okay, this is going to be our C parameter that's trainable. Okay. And now that one. Notice here we do the thing that we had discussed, which is to tie that parameter to the optimizer. So you can see optimizer infer. It takes torch, optim, atom, and we're going to be tying Z to the optimizer, which means that that's what we're going to, update, right? And the learning rate here is going to be 0.03. So we set that up. Then here, this one is important. So I'm going to introduce it. So far, you may have come across this already, but so far in the course, we've always had fixed learning rates. What I mean by that is we set the learning rate was 0.003, and it's just going to always be 0.003. However, as it turns out in machine learning, sometimes it's better to have what is called an adjustable learning rate. And what that means is that the learning rate might start at 0.003, but then it changes to 0.002, and then at some point it's like 0.001 or something. And it's something that it's smart. So the way that you do it in Torch is that you create something called a Torch Optim LR scheduler. And then you pick the algorithm, so this step LR. And so you instantiate a variable called scheduler. Okay? And the key thing is that this has to be tied to the optimizer. Do you see that? So it's tied to this optimizer over here. And then you provide some parameters, step size 40,000, gamma 0.05 there. So later on, as we're doing the train in the training loop, we're going to call scheduler, and scheduler is going to automatically update the learning rate for us. We don't have to do anything. But this is what it's like 2 or 3 lines of code, but this can have a serious impact. Whereas your learning rate gets stuck, this does not get stuck. In fact, if my loss here was not great, I could have used a scheduler too. And I encourage you guys, when you're doing step 1, to consider that. Just so far, I haven't added it because it just keeps adding complexity to what we're doing. But at this point, I think you guys can play with it. So that's how you do it. So this is the scheduler. Okay. And then here now, we can print Z and the C shape just to confirm that everything has worked out great. So notice I'm going to run print Z. What is Z? it's a tensor of 1 comma 7, so a batch of 1 of 7 values. Notice here, it's got values already, but these are obviously not trained yet, but there's 7 of them. And notice this parameter over here says requires grad equal true. Does this make sense, guys? So a lot of it is like the baby GPT, but there's going to be additional things to improve. Okay, there's quite a bit that you need to add. Okay, so that kind of completes the input part. And then now you can see here we have the next part to define is the output. So it's going to be 3 values. So the simplest thing to do is something like this, right? A target, not scaled, which is going to be a torch tensor with specific values. Like the constant that I did, or if you want to do greater than or something like that. Okay? And so you can see, in fact, that's kind of what I have here. Okay? So I just have a value. And there's several ways of doing this. Okay? But I have a value 70, 1800, and 2600. And then I have a margin out. So for instance, this 1E6, as the name implies, is 1 million. So essentially, what does that mean? From 170 to 1 million. So greater than, essentially, if you don't have a scale. But that may not be an optimal approach, but it did work for what I did. So or from 2600 to 2800, and this is the margin, 200. There's several ways that you guys could do this. I'm not saying this is the most efficient, right? But we're setting those bounds for why. How do I, and we'll conclude with this today, and then we'll pick up next week with the rest and finish it. So here, this part over here is these lower and upper bounds. So I'm generally trying to call the things related to input clamps and the things related to outputs lower upper bounds. That's just a choice. I mean, you guys can use better terminology. So how does it work in this case? Since this problem wanted the values to be, above something like this, 70, 1800, 2600, then all I do is I grab target output not scaled and I clone it. And by cloning it, what I'm doing is important to clone it because you want to separate it from the actual vector. Just in case something got updated and this gets, you want this to be a constant, essentially. So not linked to the computational graph. So that creates lower bounds glob. And then what do? I take target output not scaled plus margin out, which is this one over here, margin out, and that sets the upper bound. Do you guys understand? And you can try other approaches. You could hard code this, to be honest. I mean, who knows what your problem is going to require. But we're setting the outputs bounds and the input bounds. We need to have that somehow. Okay? And then, of course, because these are scaled, you need to standardize. Okay? All right. I think, it's 9:15. There's quite a lot going on. My suggestion, so that this is easier, although there isn't that much code left, but read through this one, okay, for next week, so that you can, we can finish this up during the first half of class next Thursday, and then we'll have our exam too. Make sense? So hopefully we'll wrap up NIO next week, and then you guys can work on your term project. Do you guys want this included on the exam? No, because it's not finished. Yeah, all right. So let's skip NIO for the exam. How about that? Not even baby NIO? All right. I'm just kidding. Yeah, that's fine. So NIO will be on the final exam, but we're not that far off. It's just there's a lot of details. So We processed a lot today. All right, so yeah, let's stop here and we'll finish this up next week.